Now that we have learned the sample analog principle from the previous video, we can set out to solve many other estimation problems besides the estimation problems for the lambda in the Poisson lambda distribution. Let's consider an example first. The simplest example is the P, the success rate in Bernoulli distribution, in Bernoulli P distribution. Suppose that your X variable follows a Bernoulli distribution, so X is a dummy variable. It follows the Bernoulli P distribution, and you want to know what the P is. Suppose this is the scenario, the following is the scenario. So you're waiting for the bus at the bus stop, and it took a long time for the bus to arrive. So you were really bored, and you reach in your pocket and you find a coin. You started to wonder whether the coin is a fair coin or not. So you want to see what is the probability that the coin will land head up when you toss it. So the X variable in that problem is a dummy variable that equals 1 if the coin that you find from your pocket lands heads up when tossed. Head up. And equals 0 if it lands tail up. So that is the random variable. It follows the Bernoulli P distribution with a success rate P. But we do not know what the P is because we do not know whether the coin is a fair coin. Now you are bored, you have a coin and a lot of time on your hand. You can collect a data set on this Bernoulli P distribution. How do you collect this data set? You toss the coin and record the value of X from that. Now, so you are bored, you have a lot of time on your hand and you have this coin. You want to know the P. So what you're going to do is to first collect a data set. The way to collect the data set is to toss the coin and record whether it is head up or tail up. So you toss the coin and record the value of X. You toss it a second time, record the second realization of X, and so on and so forth. Suppose that you tossed the coin n times, then you arrive at a data set that is denoted by xi, I equals 1 to n. So you have n observations of the coin. So that's your data set. And it's reasonable to think that this is an IID random sample from the Bernoulli P distribution. IID sample from the Bernoulli P distribution. Now with your data set, how are you going to estimate P? Well, we need to recall that for the Bernoulli distribution, the expected value of X equals the success rate. So that is something that we calculated for the Bernoulli distribution. So expected value of X equals P, and P is the parameter you want to estimate. Now by the sample analog principle, we can estimate population expectation using sample average. So a sample analog principle motivated estimator for P will be the sample average of X from your IID sample. So this is an estimator suggested by the sample analog principle. And we know from previous discussion that the sample mean is an unbiased estimator of the population expectation. So your p hat is an unbiased estimator of p. And we also know that the variance of p hat, the variance of this estimator, equals the variance of the Bernoulli p random variable divided by n. So this calculation is also something that we have done before in a different context. So that is, for Bernoulli distribution, the variance equals p times 1 minus p. So that's p times 1 minus p divided by n. So this is the variance of your estimator for the probability that the coin lands head up. And the variance, clearly it is smaller as n goes to infinity, as n grows. So the more times you toss the coin, the better idea you have about the true p. Your estimator is closer to the true p in the probability sense. So that's how you might estimate the p in the Bernoulli p distribution. Let's consider a different example. Suppose that X is uniformly distributed from 0 to C. So you know that this X variable is uniformly distributed from 0 to C, but you do not know C. C is unknown. Suppose you have collected a data set, xi, I from 1 to n, that is an IID sample from the uniform 0C distribution. So I should write open, but it doesn't really matter open or closed. But in previous lectures, I was using open interval. So let's just have some consistency and use open interval. So let this xi, I running from 1 to n, be an IID sample drawn from the uniform 0C distribution. How do you use this sample to estimate C? There are many different ways to do this. One possible way is to use this equation. So for uniform distribution, we know the expected value of X equals the midpoint of the interval, which in this case is C over 2. So you know the expected value of X equals C over 2 for this distribution. So that suggests C equals 2 times the expected value. And how do you estimate the expected value? We can use the sample average to estimate the expected value. So by sample analog principle, or so sample analog principle, suggests it motivates the following estimator. the estimator C hat, that equals 2 times X n bar. So this is one way to estimate the C in the uniform distribution. There are other ways as well. For example, for the uniform distribution, so alternatively, you could also try the variance. Try using the variance formula for the distribution. The variance of X, as we have calculated before, it equals 1 over 12, the length of the interval, which is also C, squared. So that implies C equals square root of 12 variance of X. So how do you estimate the population variance? We can use the sample variance to estimate this population variance. So sample analog principle suggests the following estimators. So C hat equals square root of 12 sigma hat squared, where sigma hat squared is 1 over n sum xi minus xn bar squared. So this is a sample variance estimator. Is a sample average. So this is one form of the sample variance that can be used as an estimator for this population variance. And sometimes you might want to use an adjusted variance estimator for the adjusted variance estimator for this using this sample, which is x squared, which is 1 over n minus 1 sum of xi minus xn bar squared. So these two estimators are almost the same except the constant in front of it. So this estimator is unbiased for variance of X. So this estimator has the property that it is unbiased for the population variance. This estimator, as you can see, because it used the division by n instead of n minus 1, it's slightly underestimating variance of X. But either way, the C hat and C hat S, so C hat V and C hat S, these two are not unbiased estimators of C because it uses this nonlinear function, square root function. It's a square root function of the variance estimator. So even when the variance estimator is unbiased, square root of it is no longer unbiased for the square root of the variance. But even though they are not unbiased, they're perfectly reasonable according to the sample analog principle. X and T, before doing the calculation, we actually do not know which of these estimators are better in terms of bias, variance, and mean squared error. So I'm going to leave a homework question for you to calculate, to simulate, to do a Monte Carlo simulation for the bias, variance, and mean squared errors of these three estimators of C for the uniform 0 to C distribution. Now, sometimes, actually a lot of times, we are interested in the distribution of a random variable, but we do not know, or there is no reasonable candidate for the distribution function of that random variable. So that is, we are in the situation with unknown distribution. So F is unknown. F is unknown, but we are interested in some features, some traits of F. For example, we might be interested in the expected value of X. Expected value is a trait of the distribution, right? So it is one summary quantity of the distribution. So we want to know some aspect of the distribution, for example, the expectation. How do you do the estimation? Now, again, we can use the sample analog principle to come up with estimators. Let's consider an example that is relevant for the present time. So suppose that the X variable that we study is the number of infected cases generated by a random infected person of a virus, say the SARS-CoV-2 virus. So X is the number of people that an infected person infects. And this random variable is of great importance in epidemiology in studying how this virus transmits among the population and in assessing how difficult or how easy the disease transmits across the population. There are two particular features. So the whole distribution is important. The whole distribution of X variable is important and useful. But in particular, there are two features that are very important. One feature is the R parameter, which is the reproduction rate. The reproduction rate, if you have been following the news, you have heard of this reproduction rate a lot. So this R is the expected value of X. So it is the expected number or average number of people that a COVID-19 patient infects. And you might heard of R0 and R without the zero. R0 is the reproduction rate in the population that had not been exposed to the virus. So R0, you can think of it as the reproduction rate at the very beginning of the epidemic. Well, R is the reproduction rate at the current population, in the current population. So that's one feature of F that is very interesting and gets a lot of media coverage. And another feature of the distribution of X that's interesting is the dispersion of X. So R tells us the average number of cases that one case generates, but it doesn't say whether, so suppose that R equals 3. So on average, one infected person will infect 3 more other people. But that's an average number. But average number doesn't give us the whole picture. It doesn't tell us whether every infected person will generate 3 more. Or most people don't infect anybody, but just there are a few who are super spreaders who will infect thousands of people. So both scenarios are consistent with R equals 3, but they are very different scenarios from an epidemiology point of view. And K is a parameter that tries to distinguish these two different kinds of scenarios. So K, what is the definition of K? So when you read the news, you will see the K number in some of the news articles, but none of the news article will tell you what this K actually is. So I did some research and I dug out this formula for the dispersion K. And the K number, the K value, is in fact this simple function of the expectation, which is R, and the variance of X. So it's R squared, which is the expectation square, divided by sigma square minus the expectation. So I should probably just write expectation because R squared sounds like something else in econometrics. So I'll just write expectation of X squared divided by sigma squared minus expectation of X. Here the sigma squared is the variance of X. So notice that I use the subscript F for the expectation and the variance. This is just to stress that F is the distribution of X. I'm taking the expectation using the distribution function F and taking the variance using the distribution F, and then taking the variance under the knowledge that X follows the distribution F. Of course, F is not known. This is just the definition equation. So sigma squared is also not known. K, R are not known. So these are unknown parameters that are very interesting for epidemiology, for understanding the transmission of the virus, of the disease. So how do you estimate this R and this K? First of all, you're going to need a data set, a random sample. Suppose you get a random sample, sample of infected cases, infected people. Of N, so you collect data on N randomly selected infected people, and your contact tracer did a good job and traced all the other cases that are infected by these cases. So then you have a data set from the distribution of X. So you have a data set of X that is Xi, I running from 1 to N. And this, let's say it is an IID sample of X or IID sample from F. Then how do you estimate this R value and this K value? That's not very hard. We can appeal to the sample analog principle. And that principle suggests the estimators R hat equals the sample mean. Well, the sigma squared can be estimated just as in this case, can be estimated using either this unadjusted version of the sample variance or the adjusted version of the sample variance. Because this adjusted version is unbiased, so we'll just talk about this one. We'll just focus on this one in the future. So that also suggests that Sx squared can be used to estimate the variance. Yeah, so correct, sorry. So that's x squared, which is 1 over n minus 1 sum of xi minus xn bar squared. So this is an estimator for R, for the expected value of X, and this is an estimator for sigma squared. So you have an estimator for all of these quantities. You can plug them in and get an estimator for K. So that will be the K value, the sample analog estimator for the K value. And is this K value or R value, are they good estimators or bad estimators? Well, you can immediately see that this R value estimator is an unbiased estimator. Its variance drop with n at the rate 1 over n. And as to the K value, it's pretty clear that this is not an unbiased estimator for K because it's too nonlinear. It's got too much nonlinearity in it. So this is not an unbiased estimator of K. But it still have some good properties, which we'll talk about in the next video.